Okay, so before we move on, I also wanted to kind of like erase everything and just show you another way to look at orbital diagrams. If we were to take the electron configuration here, you can fill out the electrons by, of course, having an arrow that shows energy. As you're increasing in the orbitals, you're increasing energy here. So 2s is lower energy than the p orbitals. And then I just fill this out. This is going to be very important because we're going to be using this to help us understand valence bond theory, which is what we're going to get to next. So these atomic properties help us basically learn more about different theories, like I said, the separate and valence bond theory, and we're layering these theories together. You also can talk about molecular orbital theory, but it's just harder to visualize, so we focus mainly on valence bond theory, okay, folks? So with valence bond theory, we know that atomic orbitals are mixing to create brand new orbitals called hybrid orbitals. And that's going to be based on the type of bond that carbon is creating. So let's go ahead and write our atomic orbitals for carbon again. We have energy, we know it's going to be 2s, and we had p orbital, p orbital, p orbital. Now let's focus on that same carbon, that CH4 molecule, and we know that carbon has hydrogen here, towards you, one going in the back. Okay? And we'll talk about that as well. Because when we're talking geometry, let me just go ahead and throw that in there. We're talking geometry, not only are we talking about the bond angles, we're talking also about the plane that each of these atoms that are attached to carbon are in. So hydrogen here and the hydrogen here are in plane. That's why you just see the plane straight lines. But we have one hydrogen that's coming out towards us, and then one hydrogen that's going to be behind the page. So sometimes they call it page, just so we can be in orientation. You can say, okay, this is like the y-axis, this is going to be the x-axis. We have the z-axis coming out of the page towards us, and then one going into the page, which you see here, okay? And the way we denote that is usually going to be a wedge, right there. So we have a wedge when it's coming out towards you, and of course, when it's going back into the page, we have a dash line, okay? And again, instead of writing it flat like this, we can go ahead and write it to give us that tetrahedron shape, all right? So that's just a little tiny bit review, which is why you can go to previous information once again to get that little bit of review. All right, folks. So what happens to create a hybrid orbital? Again, we have our electrons here that we're trying to, of course, create 4 bonds for the CH4. So that means if we're creating 4 bonds, we're going to need 4 orbitals to create those bonds. We need 1, 2, 3, and 4. These 4 orbitals are now going to create 4 brand new orbitals that are called sp3 orbitals. So if they're creating something brand new, that means that these sp3 orbitals have completely different shapes. We know the s orbital is usually like that spherical shape, and the p orbitals are dumbbell shape. But these sp3 orbitals don't look like that, okay? They have a different shape. Again, they have a different amount of energy, but of course, they're all energetically the same. So if I have all of the ability for these electrons, let's go ahead and put all 4 in here. 1, 2, 3, 4. It's easier now to visualize. Here's where a bond can happen. 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 Versus having 2 electrons empty here, 1 here, and 1 here. Now, using valence bond theory, you can go further and look at, of course, molecular orbital theory as well. Helps us kind of visualize and see clearly how these carbon is able to make those stable bonds, right, folks? So I just want to make sure that we're kind of looking at that as well. Now, if you're making 4 bonds, it's going to be sp3. 2 bonds is going to be sp2. And if it's making a 3 bonds, as you can see, which is going to be a triple bond, is going to be sp. But when it came to valence bond theory, I just want to review this as well. Not only did we get an understanding of covalent bonding, but we also got an understanding of really what a double bond and triple bond truly is. So anytime you see these single bonds here, valence bond theory allows us to say that these are called sigma bonds. Okay? And anytime you see a double bond, you have to have a sigma bond and brand new type of bond called a pi bond. They're coming from those p orbitals. Okay? And usually the sigma bonds are coming from the s orbital. And then you have your triple bond here. You always have to have a sigma bond, and then you're going to have 2 pi bonds. And so valence bond theory allows us to understand that as well. So when I'm thinking about that, I'm like, okay, let's go ahead and talk about single bonds, triple bonds, and double bonds, and let's relate it to what we know. We normally just write these lines, right? Okay, double bond, or that's single bond, or we write, okay, this is a triple bond, and that's a single bond, and that's fine. But we want to make sure that now we're understanding that these are sigma and pi bonds coming together to form these double and triple bonds. Just adding layers of information just to make sure that you understand those details, okay? So what do we know right now? According to valence bond theory, atomic orbitals are going to mix to create hybrid orbitals. That's the reason why carbon can have a maximum of 4 bonds. Okay, that's the reason why. And of course, these hybrid orbitals are going to be sp3 when carbon is making 4 bonds. And why are there sp3? Let's get into more details. 4 bonds, we need 4 orbitals. So there's 1 s orbital and then 3 p orbitals that we're using. So 1 s orbital and then 3 p orbitals that we're going to use. You saw that. Okay. And so the cool thing about hybrid orbitals is you can literally just count the amount of atomic orbitals that are going to help you figure out the amount of bonds you need. Now let's look at these carbons over here. Let me just erase all this again. Look at these carbons over here. Okay. This carbon again is sp3, so we know each bond that it has here is going to be sp3 orbital here, sp3 orbital here, sp3 over here. We need 4 bonds, so we need 4. Here, most folks will say, well, we need 4 bonds here too. But remember, when it comes to single, double, and triple bonds, they're seen as 1 electron group when they're surrounding a central atom. Okay, so we're thinking about Lewis structure there. So again, we have to layer all of our information from previous theories, right? So as you can see, I'm like, okay, well, this is an electron group, so that's 1 orbital I'm going to need. I'm going to need another orbital here, another orbital here. So I'm going to need an s orbital and then 2 p orbitals. So that's how I get sp2, because there's 3 electron groups surrounding the carbon. So it's almost like layering again. Lewis structures theory, we're layering the separate theory and valence bond theory. Okay, so we're putting them all together. sp. As you can see, this triple bond is considered 1 electron group. So we have 1, 2. So we need an s orbital and 1 p orbital. That's how we get our sp hybridization of this carbon atom. Okay. Now, of course, if it has a different shape, that means it potentially can have different bond angles and everything like that. And so luckily for us, everything kind of connects. When it's sp3 or it's tetrahedral shape, it's going to have 109.5 degree bond angles again. When it's trigonal planar, it's flat. And so that means that your hydrogens are going to be in plane, okay? And it's going to be 120 degrees here, 120 here, and 120 here. Remember, we're talking about the carbons themselves. So yes, they're showing us a single bond between 2 carbons, double bond, and triple bond, but we're still focusing on the individual carbons themselves and how they're being attached, okay? Also, we have our triple bond here, so everything's in plane, it's linear. That's going to be 180 degrees there. All right, folks, so we'll continue this conversation in the next video.